The AI revolution changed how we write, code, and think. But the next massive frontier isn't happening behind a screen. It's happening in the physical world. The next revolution is robotics. Robots have already started entering our factories, our streets, and our homes. But for a robot to safely navigate our world, pick up objects, and assist humans, it needs one critical capability above all else. It needs to know how to see. This is where computer vision comes in. Computer vision is the absolute backbone of modern robotics. It is a technology that teaches a machine to process visual data and perceive the world exactly like a human. If you want to be a part of this next physical tech wave, you need to understand how machines process vision. But if you try to learn it today, it can feel incredibly overwhelming. Should you learn classic image processing, or deep learning, or MediaPipe, or even YOLO? In this course, we are cutting through the noise. I have built a complete step-by-step roadmap to take you from the absolute beginner to mastering vision applications. Here is exactly how we are going to do it. Phase 1 is basic vision. You will master classic image processing with OpenCV. We will manipulate pixels, isolate colors, and detect edges to build your core foundation. Phase 2 is real-time vision. This is where things get fast. Using lightweight, highly optimized AI models, you will build applications that track faces, body poses, and hand gestures in real time. Phase 3 is AI vision. This is the cutting edge. We will dive deep into learning text recognition and image semantics to teach computers how to read and truly understand a visual scene. By the end of this course, you won't just understand the theory, you will have a portfolio of working projects. Best of all, the entire course is 100% free right here on YouTube. So let's get started. If you would like to level up your computer vision skills, do check out our premium courses that are available on our CV Zone platform. Links are in the description. So without further ado, let's get started. How does a machine actually see an image? To your brain, looking at this cat is effortless. Your eyes capture the light and your brain instantly tells you it's a cat. But a computer doesn't have eyes or a brain. To a computer, every image is just a massive, incredibly boring spreadsheet of numbers. When you pass an image into a script or an AI model, you are passing a matrix. Let's look at how this matrix is built. Let's start simple with a grayscale or a black and white image. A grayscale image is a 2D grid. Every single tiny square is a pixel and each pixel holds a value from 0 to 255. 0 represents pure pitch black, while 255 represents blinding white. Anything in between is a shade of gray. So a light gray pixel might be 200. And a dark gray pixel might be 50. That's it. A black and white image is just a single 2D grid of numbers. But what about color? To handle color, we use RGB instead of one grid. The computer stacks 3 separate grids together, one for red intensity, one for green, and one for blue. We call these channels. By mixing different amounts of these 3 colors at every single pixel location, a computer can display or read over 16 million colors. In programming terms, we call this 3D stack of grids a tensor. Now that you know images are just numbers, you can see why old-school computer vision failed. For decades, software engineers tried to write strict manual rules to detect objects. They wrote code saying, if you see a circle of dark pixels next to another circle of dark pixels, it's a pair of eyes. But think about how fragile that is. What if the person turns their head? What if they wear sunglasses? What if a shadow falls across their face? Even a single number in that matrix changes completely, and the manual code breaks instantly. The real world has too much variance. Changes in lighting, angles, and scale for human engineers to write rules by hand. That is exactly why we use deep learning. Instead of writing the rules, we feed AI thousands of image matrices and let the neural network find the mathematical patterns itself. Now that you know how the data works under the hood, it's time to start writing some actual code. So before we begin, we need to install two things. One is Python and the second one is our IDE. You can use pretty much any IDE you want. I prefer PyCharm, so I like to use that. Now, what we can do is we can go to python.org, and here in the downloads, we can go to all releases. And if we go there, you will see these different versions of Python, and here you can decide which one do you want to install. Now, what these mean, end of life means that there is no updates, no security updates, no bug fixes. So just security means that only the major security features will be fixed. Bug fixes will not happen. So these are kind of old. And here bug fix means that it will get bug fix as well as security updates. So right now, if we look at 12 is right about till 28, and 13 is right about at 29. So until 29 it will still work. So I believe 13 or 14, you can pick one of these. And these pre-release or feature, these are kind of risky. So instead what we will do is 13 or 14. So we will be using 13. Now you can simply go here and pick and just download. You can click on that, and then if you go down, you will see here you have the Windows installer. So 64-bit. For Mac OS you have this installer. So it's better to just use the installer here. Just download that and install it. The second thing we need is the PyCharm, which is the IDE, Integrated Development Environment, which means it is like a notepad but with advanced features. A notepad, when you write code in it, it will not tell you you did a mistake. But an IDE, it will tell you, okay, that is something not integrated with Python. You need to add a space here. You need to go down a line and stuff like that. So this is basically the advantage of using something like this. So, and one major thing with PyCharm is that it handles virtual environments. So a virtual environment in which you install all the libraries. You should not install it on your global environment, which is your PC. You should make a container, a box, and inside that you should install everything related to that project, because you might have different projects that need different packages, versions of different libraries. So it's good to install it in one box, and then that box is called virtual environment. So PyCharm handles that for you. It will create that virtual environment, and it will make it very easy for you to download, install, and create those environments and run your code. So I prefer this IDE. Anyways, so you can simply download and install. So once that is done, let's move on to the next part. So here we are in our new project, and we are going to call it Modern Computer underscore vision. And here you can see that we have selected Python 3.13, which means 3.13. So we will create this, and there you go. This is our project. And what we have right here, as I mentioned earlier, we have a virtual environment, and here you can see that is the virtual environment that has been created by default by PyCharm. Okay, so now first thing we will need to do is we need to install our packages. So in order to run computer vision, the very basic fundamentals of computer vision, we are going to use OpenCV. Now OpenCV is an open source platform that allows you to run these different functions on your images. So we are going to install that. Now there are two ways to install libraries. You can go to settings, file settings, and then you can go to your project, select the interpreter, and then over here you can click on add, and then you can write OpenCV Python, right? So there you go, you have OpenCV Python. You can click install package here and it should install. Now this is one way. Now the other way, you can simply go to your terminal, and here you need to make sure that this terminal is not your global terminal. So you need to click here and click on command prompt, and here you can see it says virtual environment. Now you are in virtual environment, and whatever you install will be installed in virtual environment. Now the easiest way to install anything is using pip. So you can write pip install whatever the name of the package. So if you know the name of the exact package, then this is the easier way to do it. But if you don't know the exact name, you can go to file settings and then search for it. So here we can write OpenCV-Python, and this should install our package. So there you go. OpenCV has been installed. And what we will do now is we are going to go ahead and create a new folder. A directory is simply a folder, so you can click on that. And here we are going to write intro to images. So over here we are going to learn how to read and read images and videos and webcam. So here we are going to right click and create a new Python file, and we are going to call it read_images. So before we learn how to read images, we need an image to test on, right? So what I will do is I will copy a test image and a video. Now this doesn't have to be this exact one. You can pretty much pick any image that you want. So here I have this test image. This is one of the tutorials of Unity and computer vision that I did. So we have this image, right? So here it shows it's 960 by 540. It's a PNG 32-bit color, and it is 604 kbs. So we can close this, and now our task is to run it, right? So what we will do is we are going to import our library, which is OpenCV. Now what OpenCV has done is they have written the name as CV, and their newer version of their computer vision library, they call it CV2. So we are going to install, we are going to import that, and then we are going to read our image. So how you read your image is cv2.im as in image read. And then inside you have to give the name or the path of the image. So here you can see this is our path, this is our image. So it's in the same folder, so we don't need to give anything else. So we will add a string and we will simply write test.png. That's it. Now this will import the image. Yeah, it will read the image, but it's not storing it anywhere. So we need to store it in a variable. We will call it img, and then this will be our image. Now if we run this now, right click and run, you will see it finishes the process and it exits the code, but it did not show us anything, right? So in order to see the image, we have to write cv2.imshow, again image show, and then we need to give the name of the window. So the name of the window, you can pretty much write anything, right? I can write here image blah blah, right? And then we'll add a comma, and then we will write the name of the image we want to show. So this is the image, so we are going to add this variable here. So we'll write here image, and then by the way, you can press Ctrl Alt and L and it will format according to the regulations. Okay, so now if we run this now, you will see right now I have multiple screens. So in one of those screens the image popped up and then it went back down, right? Because the process finished. It is showing the image but for one frame, right? For 1 millisecond maybe, and then it shuts down. So we need to tell it to stop, wait for us to do something, right? So what we can do is we can write here cv2 dot wait key, and here we basically give a delay. So here we can say 1000, and this means 1 second. So here it will show for 1 second and it will close. But if you want it to remain open until we click something, you can write 0. So if we run this now, and there you go. So here you can see it says image blah blah on the top, and here you can see this is our image. So that's how you can read the image, whatever is on your computer, and then you can make use of that image later on to process it, to maybe find the red color, to maybe find the face and all of that, right? So we are going to look into that later on. Okay, so now that we understand the images, we are going to import or read video. So we are going to create a new file and we are going to write read_video. Okay, so the idea is very similar, But with video, it's not just one image. It's a frame, it's a sequence of images, right? It's not just one image. So if you have 30 frames per second, means you have 30 images per second. So we need to read those 30 images every second, right? So how can we do that? It's fairly easy. So first of all, we are going to write import CV2 again. And now we are going to create a video object which is present in CV2. They have made it easy for us to run it. So CV2 dot video capture. Now make sure you write capital V and then it's video capture. And then you need to give in the name of the video like we did the name of the image. Similarly, we are going to give the name of the video. So here we are giving the name of the video, which is test_video.mp4. There you go. Now again, we need to save it in a variable so we can read. So here we are going to write, this is our capture device, so we will write cap. Okay, now we cannot just say show the video. We need to run it in a loop because it is constantly running, right? So we need to constantly update the images. So here we are going to write while true, T is capital, make sure of that. Then we are going to read from our video. So we are going to write cap.read, and this will read one frame from our video and it will show us. How does it show? First of all, we need to save our image somewhere. So we can write here, let's say image. But what this does, it returns us two things, not just one thing. It returns us image. It also returns us whether it was able to retrieve the image or not. So we can write here success. So if success is true, it means it was able to read it. So we can write that if it was not successful, we can end the program, or we can end the the loop, right? But for now, we are not going to do that. We will simply show the image. So we will write cv2 dot imShow, and then we are going to give in a name. So for example, video blah blah blah, and then we are going to give in our image. So again, we have our image, and then again, you remember we need to give a delay, cv2 dot wait key. And this time around, we will try to keep it as low as possible so that it can run fast, whatever the frame rate is. So we'll give a value of 1 millisecond. So this is not 1 second, it's 1 millisecond. Okay, so let's go ahead and run this. And there you go. This is from one of our Arduino courses. So if we run that now, there you go. It runs, but then it gives us an error that it was not able to read, right? So what we can do, we can write here, if not success, it means if success is not true, which means it's false, then we can break the loop. So then it will not give us an error. It will still stop the function or stop the complete script, but it will not give us an error, right? That's the right way to do it. So there you go. And now it exits gracefully, right? We need to do things gracefully. Okay, so that's how you do. By the way, the video spellings are wrong. See, this is the advantage of using an IDE instead of just Notepad or any other thing. It will tell you right now, it's saying here there is something wrong here, so we can press Ctrl Alt and L and it will fix those errors. There needs to be a space here, there needs to be space here. If I remove this, it will give us a warning. So all of these are standards that you should follow, right? Okay, not always. You can, break the rules sometimes. Okay, so we are going to go ahead to our next part. So now we are going to learn how to run webcam. So if I right click and create a new Python file, and we are going to write read_webcam. There you go. And the read webcam is similar to how you read video. So I will copy all of this and we will paste it. Now the only difference here is what you add here. That's it, literally. So here you simply write whatever your camera ID is. So normally in most cases, if you're using a laptop, it will be 0. If you have another camera attached, a webcam, then it might be 1, then it might be 2, depending on your camera. Now I believe mine will be, I think, 2. So right now I have this camera, the one that you are seeing here. You can see it's 0. It's capturing the image from there. I think I have a webcam at number 2 as well. Yeah, there you go. This is our webcam at number 2. And so this is the idea, like you can keep it running. So if you have your webcam, it will keep running until you stop it. Now, in order to stop it, you should have something to stop it, right? You should tell it that, okay, if I press this, then it should stop, right? So how exactly can we do that? So what we do is we check if our key is pressed or not. So in order to check that, we need to write an if statement. Now this is a little bit complicated, so don't get into the technical details because we're just starting off. But for now, just think of this, that if the key is pressed, then this will happen. So here, if CV2 wait key, and we need to give the function that if the key is pressed. So in order to give that, you have to write 0xff double equals ORD, and then you give in the key. So here we are going to write Q for quit. If that happens, then break. So that's the basic idea. So now if we have the webcam running, and if I press Q, it will close it again gracefully. So that's the basic idea of how you can achieve this. If you wanted any other key, you can simply type it in, A, B, C, D, whatever key you want, you can type it in, and that will be your turning off or canceling key. So now that we understand how to import images, how to read images, videos, and webcams, now we are going to go ahead to our first part, which is OpenCV basics. We are going to learn the fundamentals of image processing. So let's go ahead and do that. So now we are going to go ahead to our exciting part, which is image processing. So these are the basic techniques that you can use on an image to do something on it. For example, if you wanted a grayscale image, you are not going to create an AI model that will convert images to grayscale. Instead, you can simply use image processing techniques to convert each pixel into a different value. So we have our OpenCV library that will help us do all of these things. So we are going to look into some basic features like color detection, shape detection, and grayscale, blurring, text, images, and so on. So how exactly can we do that? First of all, we are going to go ahead to our new folder. We are going to create a new folder, and what should we call it? We will call it a_basic_vision. And then here inside, we are going to first of all learn how to convert an image to grayscale. So in order to convert it into grayscale, first of all, we need to import the image. So we already have the template for that. So we can go to read images, and we are simply going to copy all of that, and we are going to paste it here. So just to recap, we are importing our CV2 library, we are reading our image, and then we are giving it a name and showing it. So instead of blah blah blah, we can write here grayscale this time around, right? So this will be our grayscale image this time around. Or no, let's keep this as image, and we will create a new image for grayscale. So here, after we import the image, we are going to write cv2 dot cvt color. This is basically to convert your image into different color spaces. So grayscale image, black and white, RGB, BGR, all of these different color spaces, you can move around from there. So here what we will write is that we want to convert our image, and we have some options that we can convert to. So here we will write cv2 dot. Now we will decide which color space we want to convert from and to. So we are going to say, normally OpenCV is BGR. So blue, green, red. It's not RGB. I'm not sure why they did this, but OpenCV is BGR instead of RGB. So BGR, we are going to write BGR to gray. There you go. So this will convert our image to grayscale, but we did not save it anywhere. So we will write here image gray. So image gray equals this. So what we can do is we can simply run this, but we did not actually show the gray image. We are just showing the normal image, and we are going to paste here, and here we can write image gray. This will be the new image, and then we will write here gray. There you go. So if we run this now and we get an error, so I believe it's color underscore, my bad, BGR to gray. We still have, oh, okay. So the issue is that the test.png, it's not able to find because the test.png is over here. So what we need to do is we need to go back a folder. So right now we are in a basic underscore vision. So we need to go back, and then we need to enter intro to images. So here we can write // and then we can write intro to images, and then / and then test.png. So that's how we can go to that image. So if we run that now, there you go. This is your original image. And there you go, this is your grayscale image. So that's basically how you can convert an image to grayscale. So now we are going to learn how to convert an image to a blurry state. So we need to add a little bit of blur to an image. How can we do that? So these are some of the basic computer vision or image processing techniques. So we are going to create a new file, and we are going to call it blur. So similar to grayscale, we will copy all of this and we will write a blur script. We are going to import the same image, and then over here we are not going to create a gray image, and then here instead of gray we are going to write image blur. We did not create it yet, but we will write image blur, and here we will write image blur. So how exactly can we create this? So in CV2 we have a Gaussian blur, and we need to give it some values to increase or decrease the blur. So here, for example, we are going to first of all give the image, whatever image that we are using, and then we need to give the kernel size. So this is basically how much blur do you want. So here we will write 15 by 15. This is the kernel size, and then you have also a value of sigma x. So again, these are technical values that will allow you to increase or decrease your blur. Right now you can experiment with them to see what the effect is. So here we can write image blur equals this. So now if we run this, you will see we have, this is our original image and this is our blurred image. There you go. And if we go back and we write here 3 by 3, then you will see the blur will be actually less than before. Where is the other one? There you go. This is the blur image and this is the original image. So you can see it's very slightly blurred. So that's how you can add blur to your images. So now we are going to learn how to crop an image using our OpenCV. So we are going to close these, and what we will do is we'll create a new file and we are going to write here crop. And in crop, we are simply going to copy, let's say, the blur or the grayscale, whatever you want to copy. And then we will remove the blur, and then we are going to write image crop, and then here we will write crop. So how exactly can we crop? Now, an image is just a grid. It's a table, it's a grid of pixels, right? So what we can do is we can simply crop it by giving it a number, crop from pixel this to this. So for example, crop from pixel 100 to 200, right? So we need to give it in both directions. So what we can do is we can write here image, and then inside that we can give in the value from where to where do you want to crop. So for example, the first one is always the Y value. So here we can write this is the Y value. So we have Y1 to Y2, and then comma, and then X1 to X2. So that's how this goes. So here Y1, let's say, is 100, and then Y2 is, let's say, 200. Then our X value, let's say Y1 is 50, X1 is, let's say, 50, and X2 is, let's say, 200. There you go. So now we need to save this whole part. We need to save it in image crop. There you go. So that's how you crop an image. Let's run that. And this is our original image, and this is our cropped image. You can see it's basically coming from, maybe, no, it's from here, somewhere here. There you go. So from here, if we look at the numbers, there you go. If you look at the numbers, 100 to 200. So 100 is here and 200 is here. And then for 50, 50 is from here till here is 50. And then 200 is from here, from 0 to 200. This is the x-axis. So again, I like to give you a challenge. Try to crop this image, the green parts. Try to add values and comment in the comment section below that this is the exact value from this green part till this part here, right? So give me that number, and let's see who can do that. So now we are going to learn how to add text to our images. So let's say we read an image and then we want to add a text on it. For example, this is a car, or this is red color, or something like that. How can we add text to our images? So we are going to right click and create new file, or if we are just copying, you can also just copy and paste and then change the name of it, right? So you can write, this time around we are using text, so we will write text.py. So here we have our image, we are reading it, we can remove all the crop, and we can remove the second image. So we are going to write on top of our current image. So we will simply write cv2 dot put text, and over here we have to give in where do you want to put the text. I want to put it on my image. And after that, we have lots of different variations, lots of different values. So what exactly do you want to write? So let's say we will write hello from CV zone. Let's say this is our text. And then where exactly do you want to start and end it? Start it. So we will give in a point or an origin. So let's say it's 100 and 200. So x-axis is 100, y-axis is 200. And then we have the font. So cv2 dot font. So here you can simply select which font do you want, and then you have the scale of the font. So let's put it as 1. Then you have the color. Let's say you have it's BGR, so blue, let's say green, and red, so it will be green color. So let's put it at 200, so it will be a little bit darker green. And then the thickness of the font, let's say we put it as 2. So again, you can play around with these values. Let's run it and see. There you go. It says hello from CV zone, but let's try to put it here. Okay, so let's say this is this was how much? 100? Yeah, so this was 100, so let's make it 300, and then let's move it at the top, so it will be less, so maybe 100 here, and maybe 300 here, a little bit more, maybe 350, 350, and there you go. It's hello from CV Zone. Now if you wanted to change the color, you can go ahead and change it here. So let's say you have BGR, you wanted red, you can put 200 here and you can put 0 here. There you go, it became red. Now if you want, let's say purple, I believe it's 200 here and here. Yeah, there you go. Now it's purple. So again, you can keep changing these values and try it out. Let's say I put the thickness as 10. That will be really thick. There you go. It's not readable anymore. So normally you can put it at 1 or 2 and it should be readable. So 1 is a little bit off, so you can use 2. Anyways, so that's the basic idea. You have all these different values that you can play around with them and add your text. So now we are moving on towards our interesting part, which is shape detection. So how exactly can we detect shapes? So first of all, let's go ahead and create a file. We are going to write here shapes. Now you can use OpenCV to detect shapes, but the code would be a little bit lengthy. So what we have done is we have a wrapper for OpenCV that makes it easier to perform some of the tasks like object detection or color detection or shape detection. So we are going to use that instead. So in order to install it, we'll go to our terminal, make sure it is this terminal command prompt, and you have your virtual environment over here, and we are going to write here pip install CV Zone. So in CV Zone, we have these functions that will allow you to quickly detect shapes and colors. So here, first of all, we are going to import CV2. Then we are going to import CV Zone, and then we are going to import our image. So here we are going to write image equals cv2.imread, and then we are going to give in the name of the image. Now, in order to make it easier, I have this image. Again, you can download it from our website. So these are the different shapes that we are going to detect. So we have the image shapes.png. So once we have that, we can simply show it. cv2.show, and then image, and then we can write image. There you go. So, and then we will write cv2.wait key, and we will give it a delay of 0. So if we run this now, there you go. This is our image. Now we need some processing on this so that we can easily detect our shapes. So the first thing we will do is we will convert it into grayscale. So if you remember, image gray equals cv2.cvt color, and then we give in the image, and then we give in the cv2 dot color underscore bgr2 gray. So this will convert it into gray. Now, one thing that we haven't done before is stacking images together so that it's easy to see the process. So what I like to do is I like to use image stack equals cvzone dot stack images, and then you give in all the images you want to stack. So for example, image, and then image gray. So it will show them side by side like in a table. And then you give in how many columns do you want, how many columns. So for example, we need 2 columns, and then what is the scale of each image, because if you put them together in the same scale, it will be too big. So we will make it smaller, and we'll make it 0.5, let's say. So if we run this now, we instead of showing all these different images, we can simply just show image stack. We'll write here image stack, and then if we run this now, there you go. So this is our original image, and this is our grayscale image. So now if we wanted to add more images, I can even add here another image, image gray again, and it will show us below that. There you go. So it becomes very easy to play around with this. And then if I can put 3 here, and then it will be in front of that. There you go. So it makes it easy to understand the process of the image. How exactly are we processing? Now, once we have this, we need to detect the actual edges so that we know what is the shape of it. Now, to detect edges, we have a function called canny edge detector. So we can write cv2.canny, and then we will give in our image gray, and we will give in the value. Again, these are values that you can play around with to get good results. So it's up to you to change around with these values. So we can write here image canny, and again we can simply copy this and put it here, and now it will show us the image canny result as well. There you go. So that's pretty good, right? But here we have a problem. The problem is some of these lines are duplicates, right? If you zoom in, let's make the scale 1 so you can see. So if we look at these images, there you go, it's quite big. You can see there are duplicates here. We don't want these duplicates. We just need one single line. So what we can do is we can make them thicker. These lines, we can make them thicker by using a function called dilate. So we will write here cv2.dilate, and inside we are going to give in our image canny. We want to dilate that, and then we need to give in a matrix of how much dilation do you want. So that we can give in using NumPy. It's a library for matrices, so we need to import that. Import NumPy as np. So here we are going to write here np.ones. So normally you give in just the size of the matrix, but this dilate function, it needs a row and column, a matrix of ones. So what is that? How big is that matrix will decide how much do you want to dilate. So for example, we give in 5 by 5, right? And that will give us some dilation. So we'll look into that. Is it too much? Is it too less? And so on. And then we need to give in what exactly is the integer type. So it's uint. The integer type is 8-bit. So again, you don't need to go into that much detail. Sorry, you have to write np dot integer 8. So you don't need to go into that much detail. Just it's a pattern you have to follow. And then how many times you want to iterate it. So iteration is, let's say, 1. So if you have more iterations, it will be thicker. The dilation will be more. So again, we will store it in an image called image dilated equals this. Is the spelling wrong? Yeah, dilated is wrong. So we will copy that, and now we can put here image dilated, and we can make this 4, and we can make this 0.5. So if we look at that, cannot interpret 5 as data type. Where did it go wrong? Oh, okay, so my bad. So this np1s is part of this. We need to add a bracket here. My bad. There you go. So here, there you go. Now you can see these are dilated. These are thick, edges. So now these are not duplicates. So if we go and put 1 here, we can see better that we don't have these duplicates. There you go. So now we can simply go ahead and detect the edges. How many edges does the shape have? If it has a lot of edges, it's a circle. If it has 3 edges, it's a triangle, and so on. So what we can do is, now we can simply use the CV zone function to find the contours. Contours means basically the edges. So here we are going to write CV zone dot utilities dot find contours, and inside that, now you can also import it here. You can write import CV zone dot utilities, and then you can simply write find contours here. Yeah, you can do that too. It's up to you. But anyways, once we do that, we need to give in our image, the original image, right? This is the original image, so you can draw on it, and then you will give in the processed image. This is our processed image that we need to give in. And then we need to tell, do you want to filter something and do you want to draw or not? So here we will write filter equals none, and then draw equals true. I will show you what that means. Okay, we need to write from CV zone utilities imports find contours. Now we can use find contours here. Okay, and then what it will give us back is the image contours on which the contours are drawn, and it will also give us the contour found. So basically contour found will have a lot of information inside it. Where exactly are the contours, which is the biggest one, and all of that. So where is the center of it, and this information. So let's run that now. Image contours, we are going to add it here. Let's make this 2, and let's make the scale 0.75. Let's run that. We have an issue. Draw is not okay, it's draw contours, draw con, my bad. Okay, there you go. Okay, it's not visible. Okay, so let's make it 3, and let's make this 0.5. Let's run that again, and there you go. So now you can see we are detecting all the shapes. So here it's showing 3, here it's showing 4, here it's showing 4. You see all of that, but one of them is wrong. Here you can see it says 4. Now this is a challenge for you. Make it, fix it by fixing the dilation or the color or the contours. Do something, try different values and see if you can get this right as well. But in most cases, like here it says 8, we can say it's a circle, then 4 it's a square. And then you can also check whether it's a square or a rectangle, because if the values of the contours are similar, then you can say it's a square. If it's not, then it's a rectangle. But how do you get these values? Let me show you. So if you go here and you write print contour found, and if we run that, there you go. These are the contour found, but then you have lots of information in them, right? So it's very difficult to understand what's going on. So we will get only the first contour and we will run it, and there you go. So here these are all the actual points that it gets of those lines. But what we need here, you can see this is the area of the contour. This is the bounding box. This is the center. So if we wanted just the center, we can write here center, and this will give us the center of that contour. It's 507 and 505. If we wanted the bounding box, that will give us the information whether it's a square or a rectangle. We can write here bounding box, and that will give us the bounding box information. So this is the X and this is the Y, this is the width, this is the height. So if the width and height, look at that, it's 106 and 107, it's probably a square. But if it was way apart, then you can say, okay, it's a rectangle, right? So this is a challenge for you. You can go ahead and try it out. Now, one more thing you can do is you can filter. So here right now it says none. So here we can give in an array of the values we want to filter. So for example, if I just want triangles, I can write here 3. And if I run this now, you can see here it will only show the values that are 3. And inside here in the contour founds, you will only get 3 values, right? So here I can write, I only want 4. I only want square or rectangles. There you go. So now it will only show 4. Now if I wanted 3 and 4, then I can write 3 and 4. There you go. So now it will show us 3 and 4. It's not showing us the circles. So that's how you can basically add the filters. So now we are going to go ahead and detect color. So how exactly can we detect color in images? Let's go ahead and try it out. So we are going to go to intro to images and we are going to copy the webcam. So what I like to do is I like to demonstrate instead of on an image, I like to demonstrate on a webcam because it's more fun. So we will copy the webcam code and we are going to paste it here and we are going to write color underscore detection. Now here we have the video capture 0 and we are running video blah blah. Here we are going to write color detection. And if we run this now, let's see what we get. This is the image that we are getting. There you go. This is the image we are getting. So what I like to do is I like to pick an object that we want to detect and then we can try to eliminate that. So let me bring it in. This is the color that we are going to detect and this yellow color. So we are going to filter everything out except for this color, right? So and then we move it around and then we can track it, right? So what we can do is we are going to use the color module from CV Zone. So we will write here from CV Zone dot color module import color finder. So now the color finder is very easy to use. You will simply write here color finder and inside that you will write that track bar equals true. And over here we are going to give it an object my color finder equals this. So this is our color finder now, and what we need to do is we need to run it in the loop so that it continuously finds the color. So here we are going to give in or right now it's just true, so it will just show us a track bars so that we can find the color. Once we find the color, then we can actually detect it. So let's run that. I will explain it a little bit more. So here when we put track bar equals true, it basically means we are in debugging mode. So debugging mode, we are trying to find the color, right? So here we have these values. These are basically HSV values. Like we have RGB color space, like we have grayscale color space, we have HSV, which is hue, saturation and value. Now in hue, saturation, value, HSV, it's easier to find colors. So that's why we are using this color space. So here we have two colors of hue, two values of saturation and two values of value. So what we will do is the first thing we need to do is we need to move this around and things will change. But right now on our original image, nothing is changing. So what we need to do is we need to add an update. Over here we need to add an update. The update will be, let's say this is our image color and then we have our mask and then we will tell our color finder to update my color finder dot update and then update on our image and using an HSV value. So we need to give it some HSV value, some random HSV value. So we can write here HSV value. So this HSV value we can declare here. Right now it will be nothing because right now we don't have that HSV value, but later on we can, you know, add that. Sorry, it's HSV val. And then if we run that, we move we also need to add this. We need to show this because this will be the color image that will change. So we need to show that. So we can write here image stack equals CV zone dot stack images, and then we will stack our original image and then our image color and then our mask. So we will have all three images and then we need 3 columns and we will put 0.5 as our scale. Now we can simply show image stack over here and this will be our color detected. So there you go, we have all these 3 images together, and now if I move this, you can see it is changing. So if I put my color here and if I try to move it, we need to make sure it doesn't disappear. It should stay. So we will keep changing. There you go. And then right now it's pretty good. Like we have already achieved some good results. So if I keep moving it now, there you go. So we are detecting this color. There you go. It's pretty good, right? So now, given that we have the HSV color, so this is that color. The track bar that we moved around, this is the actual color, the value of it. So we can copy this, and now here in HSV val, we are going to paste it. That's it. Now we can simply run it. And before we do it, sorry, we need to change this to false. So now we are going out of the debugging mode. So just run the original thing. So there you go. So now we are, whenever we bring it in, this is the color that has been detected. So similarly, you can do for red color, green color, blue color, whatever color you want, you can do it for. Now, one thing I like for you to try, I'll show you a simple demo of it as well. After I have detected this, let's say, then I need the position of this. How can we do that? We can do it using the image contours, right? If you remember, so let's put it together. So we will copy color detection and we will write here color plus contour. There you go. So color plus contour, and here what we will do is we will add our from cvzone.utilities imports what was it, find contours, and we will go to our mask, and we will give in the mask image to detect the position of it. So here we will write find contours, we will give in our original image, and then we will give in the mask image, and that is pretty much it. So now it will detect the contour and it will give us the value, right? So here we will write image contours and then confound equals this. Now if we put this in our stack image and we put the columns as 4 and we run it, now it is going to give us, wait, it didn't work. Oh, because we ran color detection. We need to run color contour. There you go. So now the last image, you can see it is going to give us this. There you go. Now it knows the X and Y position of this, right? So here, if I just print it out, I can write here print. I'm assuming there will be only one contour found. So I will write here confound at 0. And then give me the center of it. But sometimes when it did not find it, it will give us an error. So we can simply write if contour, if confound, then do this. If there is a contour, then do this. Otherwise, it will give us an error. So we don't want that. There you go. So as soon as you find the contour, it's giving us the X and Y position. So imagine the things we can do with this. We can basically create a color game. So if it's yellow color, draw with yellow lines, right? Then if it's a red color, then draw with red lines. You know, it will be an amazing project for this case, right? So this is basically the basics of image processing, and as you can see, it's very easy to implement. Just with a few lines of code, we have done color detection, contour detection, blur, text, and all of that. So next we are going to go into a little bit more advanced stuff where we detect faces, body, gestures, and all of that. So let's go ahead and do that.
Welcome back to the Modern Computer Vision course. So far in this course, we have covered basic computer vision, where we learned how to read images and videos, manipulate them by applying effects like grayscale and blur, cropping them and putting text over them, and then we wrapped up with color and shape detection using the HSV color space. Now we are moving into the second major part of this course, which is real-time vision. This is where things get really exciting. We are no longer just processing static images. We are going to start working with live, real-time detection systems. In this section, we will cover face detection, body detection, hand detection, background removal, object detection using YOLO, and finally training your own custom YOLO model so you can detect any object you define yourself using a dataset. So I am inside the PyCharm IDE. I will start where we left before. So we have our main directory, which is of modern computer vision, and here I will create a new subfolder with the name of b underscore real underscore time underscore vision, and I will hit enter. So a subfolder has been created for this part of the course, and firstly, I will create a new Python file that will make us able to detect the human face present in the front of webcam. So I will create a new Python file with the name of face underscore detect and hit enter. So the face detection requires a webcam to be opened so that it can detect a human face present in the front of camera. So we will paste the exact same code we have used in the previous parts of our course, and we will further add the detection logic in it. So this is the code we have used before. We have the import of CV2, which is our OpenCV library, and here we are initiating our video capture, passing the index as 0 as I am using my primary webcam of the PC, and then we have a while loop that exit on the basis whenever the user presses Q from its keyboard, and inside the main logic we are reading the webcam feed frame by frame. As we know that a video is nothing but a continuous stream of images, so likewise webcam work in that way, and here we are showing each frame in a continuous manner using this loop. So we will execute this file to see that if it is working right or not. So this is the OpenCV window. You can see that over here is the label of face detection, and my face is visible in the front of webcam. And now we will add the face detection logic so that it can detect my face, and also it will tell us the confidence of the detection, like it will tell us it will tell us the percentage that how much this thing resembles the human face. So currently we will stop execution of this file. Then we will go towards our next import, and the import we are doing is of CV zone library. We have used CV zone library in our previous part. So here we are again CV zone because it provides us modules like face detection, body detection, hand detection, selfie segmentation, and more. Most of the features of CV zone you have seen in the previous parts. Here we will use it for object detections we have mentioned at the start of this section. So from the CV zone we will target the face detection module. So it is available with the name of face detection module. We will hit enter. But we can also do another thing, like instead of importing the whole module, we can import the class that will able to create a detector. But here instead of importing the whole module, we can import the specific class that is responsible for face detection. So we will edit our import like that. From CV zone face detection module, we will import our face detector class, and down in the code we will use this face detector to create a detector object in our current working file. So I will add some spaces, and here I will create an object, and here I am initializing the face detector class. This face detector enables us to load a pre-trained face detection model provided by MediaPipe face detection. As you know that CV zone is built on the top of OpenCV and MediaPipe. So when we will execute this file, the face detection module or the face detection model will be downloaded automatically inside our current working directory. It is provided by MediaPipe, so we will not go into the deeper details, but for the enough knowledge, I am telling that this face detector loads the pre-trained face detection module or the face detection model, and inside our while loop, we will add a new line of code after reading the frame, and the syntax of that line of code will be like image and the bounding box. As we have to draw a bounding box, so that's why we are extracting the bounding box from the detector, which is returning to us, and we will use the detector object we have created as above, and the method we are going to use is the find faces. So it will target the frame as we are reading the frame inside this image variable. So we will pass that img inside this find faces method. So what this line of code is doing, it is passing the current frame inside this find faces method, and it is returning the edited frame or the manipulated frame by this detector, and also the bounding box around the region where the face is detected. And after that line of code, we have an if block that if the bounding box have been detected, that means the detector is successfully able to detect a human face. Then we have to perform this certain thing, and that certain thing is that enter equals to bounding box, and we are targeting the first face detected by the detector. So there can be multiple faces visible in the front of camera, like a person is sitting with me. So we are just targeting the first person because this bounding box is a list, and it gets the list of faces from this detector. We are only targeting the face that is present on the 0th index. That means that 0th index means the first face, and as it is a dictionary, so 0th index is the key where we are targeting, and the value we need is the center. And now let us execute our file to see what we have now. It is saying that no MediaPipe is found because, as I have said, that CV zone is built on the top of OpenCV and MediaPipe. Previously, we have installed the OpenCV but not the MediaPipe, so we have to go towards our terminal, and here we have to type pip install MediaPipe and hit enter. It start installing the MediaPipe library for us, and then we will able to run our file successfully. Now MediaPipe has been successfully installed. You will be thinking why we need MediaPipe, as we know that CVZone is built on the top of MediaPipe. So CVZone needs MediaPipe as its dependency. So we have installed it, and now we will execute our file. You can see that it is saying that downloading MediaPipe. Let me first close this and see what we have in the terminal. You can see that it is downloading the MediaPipe face model, and then it is showing download complete. And if we notice in our working directory, we can see that this blaze underscore face underscore short range .tf light model has been downloaded. So this is the model provided by MediaPipe for face detection, and whenever we execute our file for the first time, this model is being downloaded. Next time file will use this model for detecting the human faces. So let us see what we have in our output. You can see that my face is detected, and it is drawing a bounding box around my face, and along with that it is putting the confidence score of telling how much my face resemble the human face, or you can say that how much this object resembles the human face. So this is how we perform the face detection with this line of code. You can see that we have less than 15 lines of code, and we are successfully detected the human face present in the front of webcam. Alright, now we are moving on to the hand detection, and what we are doing here is we are taking our face detection code and editing it to work for hands instead. Same structure, same flow, and we are just swapping out the import and the detector we have. Currently we have the detector as face detector, and in the new file we are going to create, we will use the hand detector. So I will copy this code, and from here I will create a, or better to say, inside this subfolder I will create a new Python file with the name of hand underscore detect and hit enter, and I will paste the exact same code. Instead of a face detection module, now we will target the hand tracking module. So the name of that module is hand tracking module, and from that module we will import our hand detector. So the names are pretty much same. The first one was working for the face, and currently this hand detector will detect the hand visible in the front of camera. Currently we are just focusing on one person. What does that mean? The previous file you have seen that we detected only one face. No matter how many persons are present with me, it will detect only one face. So in this hand detection script, it will detect only two hands. We will see after editing the code. So we have to edit this detector also. We have to use the same name, and now it is working for creating a detector for hands, and for that we have to pass the parameter of max hands as 2, because we have to detect the two hands because a normal person has two hands. And also we can pass a parameter of detection confidence with the comma, and the detection confidence would be, let's say, 0.8. so in percentage it will be 80%. So what we are saying to our hand detector, that you have to detect the hands that have the confidence more than 80%, and you have to detect the maximum two number of hands. And if we go down below, here we have our previous code in which we are finding faces. Now we have to use the accurate method provided us by hand tracking module, and the name of that method is find hands. It will find hands inside every frame passed to it, and we can also rename this variable as hands. We are getting the hands outside of this find hands method. And now instead of focusing on the bounding box list which we used in our previous code that was responsible to accumulate all the faces present in the front of camera, now we are concerned with the hands. So if we get the hands out of this find hands method, hands is nothing but a same list as bounding box we used in our previous code. And the more tweaking in the code is that we rename this bounding boxes as img, because we no longer need bounding boxes. And inside this if condition we have to edit some code. Let's say we currently backspace, and if we detect hand present in the front of camera, what we have to do, we have to create two variables as hand1, and inside that we are getting the hand we got as 0th index. So 0th index is the first hand present in the front of camera, and below that we will add a new line of code with lm list equals and 1, and inside that I will target the dictionary, and the value will be lm list. So what this line of code is doing, lm list is the landmark list returned to us by this find hands. So we have stored that list inside this hands, and then we have checked the condition. If something is present inside that list, we have to target the first value present inside that list, and that list is a list of dictionaries. So we are manipulating our first entry which is present at 0th index, which is hand1, and in the key value pair we are targeting the lm list, which is the landmark list, which is the list of 21 landmark points on our hand. Each point gives you the x, y and z coordinates of the specific joint we have on our hand. So the next line of code we have is the hand type, and if we press tab we can see that it is completing code for ourselves. This is the benefit of PyCharm. This line of code tells you whether the detected hand is left or the right hand. MediaPipe determines this based on the orientation of the landmarks. And the final thing we can edit in our code is this hand here. So we will execute our file to see if we have the successful execution or not. You can see that it is downloading the hand model, and it will also appear there. So this is the hand detection window, and if I put my hand it is giving me an error that let us see in the code what is trying to say. So we are passing the hand type. This is the not actual value in the key value pair of hand 1. Its actual name is type. So we have to target the type. It will give us the type of hand. It will be either it will be right hand or either it will be left hand. So we will execute our file again to see that if we have the successful execution or not. So this time you can see that it is not downloading the model because it has downloaded the model at first. Whenever you execute the file for the first time, it downloads the model and later on uses the same model. So let us see our output, and if I put my hand in the front of camera, it is detecting it. And here is my second hand. And also a green dot is appearing, and wherever I take my hand in the front of screen, it is tracking it successfully. So this is how CV Zone makes us able to detect the hands present in the front of camera. Now we are doing body detection, and we have to do the exactly same thing we did last. We have to copy the previous hand detection code and paste it into a new file, and then we have to change the lines of code that will be responsible for showing the body instead of hands or face. So we will copy this hand detection code and we will create a new Python file inside our real-time vision directory, and we will give that name as body underscore detect and hit enter. So we will paste that code, and after pasting the code we have to change the things. So the first thing we have to change is this module. Currently we need a module that is responsible for detecting the human body, and that module name is pose module. And from that pose module we have to target the exact class which is named as pose detector. And after making the correct import, we have to change the name of our constructor, and let me change it accurately. Control V, and there is no need to pass the parameters this time because we are pretty much done with our detector object that is responsible for detecting a human body. And let us move towards our main code which is inside this while loop. And the main thing, we have this find hands method. We have to replace it by find pose method which is provided to us by this pose detector class, and inside it we are passing our raw frame. Currently what we will do, we will only get the processed frame out of this find pose, and in the next line we will extract the landmark list of all the 33 landmarks of human body. So as the human face and a human hand has the landmarks, so likewise the human body has 33 landmarks. We will extract it along with the bounding boxes. The same method we have applied in our face detection module, and this time we will use the same object we have created here, and we are calling the method as find position. We'll return the list of landmarks along with the bounding box being drawn around the body. So every major joint on the body will be highlighted with the green dot. We will see it later. And this B boxes is a dictionary containing the bounding box around the detected body. These are two different methods you have to focus. First one is the find pose, which is responsible for detection and drawing, and then we have this find position method that is responsible for giving you the data which it has extracted from the frames present in the front of camera. So in short, it is responsible for drawing the bounding box, and it is responsible for getting the data what is present in the front of camera, a human body or any other object. For any other object, it will not draw any bounding box or it will not draw any landmark, but for a human body, this method gives the data inside this bounding box. I did this whole code block as center, as we have to target the center of our body, and again the same is at bounding box, and from the dictionary we will target the center of the body. We can also write the 0th index with here, but this is redundant. because we can see that inside our face detection module we are targeting the 0th index, and also we are targeting the value as center. We are targeting the center of our face, and we are doing the same thing with the body, but there is no need to add this index. We are only detecting the one body. If you don't pass the 0th index, it will by default detect the body present in front of the camera. And I think we are pretty much done with our code. The last thing we need to update is the name of our window, which is body detection. And whenever we execute this file, it will download the MediaPipe model, which is of human body detection. And let us see what is the name of that model by running this file. So this is running, why it is running face detection? Let me see. If we are running a wrong file, we have the our body detect file from where it has come. Let me delete this and let us skim through the file why it is running. So body detect, let us execute this file again. So now you can see that it is downloading the MediaPipe pose model, and you can see that a bounding box has been drawn in outside my body, and also the landmarks are being drawn on my hands, on my face landmarks, and also all other joints. So it is drawing the landmarks on my face, the joints of my hands, my shoulder joints, my elbow joints, and if I stand, you will get a less voice, so you have to compromise on my voice. You can see that so it is successfully detecting my all body landmarks along with my knee joints and also my toe. So whatever the 33 landmarks are being described by MediaPipe, it is detecting all those landmarks. And if we see in our directory, we can see that post landmark.task model has been downloaded. So this is how we perform the face, hand and body detection with the minimal 15 to 16 lines of code. Now we are moving into the most exciting part of this section, which is object detection using YOLO. For that, we will create a new Python file by clicking our subdirectory, which is real-time vision, and the name of Python file we will pick as object underscore detection and hit enter. So as I have told you that we are using YOLO for object detection, and Ultralytics is the company that develops and maintains the YOLO models. So what is YOLO? YOLO is written like this. It stands for you only look once, and it is one of the most popular and widely used object detection models in the world. The reason why it is so popular because it is fast, accurate and surprisingly easy to use. So we have to import this YOLO class from the Ultralytics package. Ultralytics import YOLO. By default, this YOLO comes pre-trained on a dataset called COCO, COCO, which contains 80 different object classes. That means straight out of the box without any training, YOLO can detect 80 types of objects, things like person, car, bicycle, dog, cat, laptop, chair, and many more objects. But there is also an advantage of YOLO. You are not limited to those 80 classes. You can train YOLO on your own custom objects. So if you have something that YOLO does not know, let's say a specific product or a logo or any custom object, you can train it to detect that too. We will actually do that later in this section. So currently you can see that it is showing me an error or the red warning that this package is not found. So we have to install this package. As you know, we can easily install it by going to our terminal and also from these Python packages. If we write Ultralytics, you can see that it is appearing. And also we can go to our terminal and using the pip command like pip install Ultralytics and hit enter. It will install the Ultralytics library for us, and from that we will use YOLO. So let us wait for its installation. It takes few minutes. Now the Ultralytics library has been successfully installed and the red warning has also been disappeared. So let us go towards our next import. We have of CV2, which is OpenCV, for starting the webcam and reading our frames. And the third import we need is the import of CV zone, the library that is used to draw the bounding box and the label of the detected objects. As we know that YOLO is pre-trained over a COCO model that is able to detect 80 objects by default. It includes person and water bottle, chair, laptop, and all the other things. You can go to YOLO documentation and see the names of other classes. So we will paste the basic code we have of our camera initialization. It will start a webcam. We have our video capture, our while loop, and in this time we have given the name as object detection to our window. Now we will add a important line of code, and that is creating our YOLO model. We are not creating, as YOLO is a pre-trained model, we are initializing our model. So we will call the constructor, as we have imported this YOLO class, and inside it we have to write the name of the model we are using. So we will write it like YOLO26s.pt. So this is the model file we will be using. Whenever we execute this file, this model file will be downloaded automatically from the internet inside our current working directory. So the 26 is the version of YOLO. YOLO comes with various versions. The previous versions are YOLO 5, YOLO 8, YOLO 11, and the latest one we have is this YOLO 26. So we are using the latest one, and this S represents the type of the YOLO model. Other types of the YOLO model we have, let's say we remove this S from here and we write N. This N stands for nano. It is the smallest and the fastest model by YOLO, which provides lowest accuracy, and we are using the variant with this S, which is YOLO 26S, which is small. It is good for a balance of speed and accuracy. And the next one we have is this with M. It is the medium model provided by YOLO. It is more accurate, but it is bit slower. And also the other one we have is the YOLO 26L, which L stands for large, and it provides high accuracy but needs more computation power. And the extreme large, or the most accurate model provided by YOLO 26 is X. It is the most accurate, but it needs high computation power, and our processing will become eventually too much slow. So we will rely on our small model YOLO 26S. So let us execute this file so that this model should be downloaded in our directory, and also we can check our webcam. As you can see, it is downloading the YOLO26.pt file in our current working directory. That is the model we will be using for default object detection. Currently we are performing the default object detection. So whenever we open the webcam, it will detect all the objects that has been defined inside the COCO model of YOLO. Currently it will not detect because we have not used the model anywhere. We currently initialize it. Later we will use that model inside our while loop so that we can perform the object detection. So let us wait for this download. You can see that it is downloaded as 80%. And now that you can see that this model has been downloaded 100%. If we see, you can see that it is located inside our current working directory. So our webcam has also been opened, and let us add some code so that we can use our model to detect the objects, and we will see further objects which the YOLO can detect. So for that we will add a line of code to run our model. So below this frame reading, we will create a variable as a results, and we will use our model which we have initialized as above, and we will pass the image or the frame we have to process. And also the second parameter is stream, and its value is passed as true. So img is our current frame which we pass at every execution of our loop, and the second parameter is of stream. that tells the YOLO to process this as a stream. That means instead of loading everything into memory at once, it yields the results one at a time. This is much more memory efficient for real-time video, and this approach is recommended. So results is nothing but it will act as a generator. It does not hold all the data at once, it produces it on demand. So we have to iterate our results, and we will use a pointer like r. For r in results, what we will do, we will run a for loop, and inside that for loop we have another nested for loop as for box in r dot boxes, and inside that we will write our code. So this r dot boxes is a collection of all detected objects in each frame. So each box represents one detected object. So if YOLO detects 5 objects in the current frame, this loop runs 5 times. And inside that we have this line of code like x1, y1, x2 and y2 is equal to map of the bounding box we have. This box dot xy with the index 0 gives us the bounding box coordinates in the format of top left corner and the bottom right corner. So this x1 and x2 represents the this x1 and y1 represents the top left corner where the bounding box will be drawn, and this x2 and y2 represents the bottom right corner. So we are wrapping that inside this map because YOLO returns the data in floating point numbers, but we need into integers, so that's why we are mapping it whatever we got from YOLO. So what we have this results what we are getting from this model, and inside the traversing of that results we have a nested for loop where we are extracting the data, and data is the each bounding box of every object present in the frame. So this is the spelling I have written wrong, let me correct it. So this is the accurate one, and in the new line of code we will have the width and height equals x2 minus x1 comma y2 minus y1. Here we are calculating the width and height of the bounding box. So w gets the value as x2 minus x1, and this height gets the value from y2 minus y1. So let us execute our file once again. It will not show the result yet, but it will confirm that we have written our code correct and there is no error. So let us execute this. You can see that the webcam has been started, and also you can see that it is providing the data. You can see in the terminal it is detecting a person, but we are not drawing any bounding box around that person. But in the terminal you can see that the person has been detected. So let us write the code so that we can draw a bounding box along with the label of the object that has been detected. So for that, first we have to draw the confidence of the object that has been detected. So we will use a variable as conf equals bounding box we got, and we are extracting its confidence at the index of 0, and as it is returning a floating point data, we will wrap it inside an integer standalone function so that we get the integer data. So it will return the data between 0 and 1. So for getting in the percentages we have to multiply it by 100. So it will provide us the confidence score, the value between 0 and 1, and it tells the confidence of the YOLO model over the object that has been detected. And in the next line we have to detect the object with as CLC stands for class. As I have told you that YOLO depends on 80 built-in classes, so we are using the variable name like that. So we are extracting the class like that. And in the next line, after extracting the class, we have to mention the name of the class. Let's say the person has been detected, or a laptop has been detected, or a book has been detected. So we have to get the name. So we will call our model, and inside this names list, we will get the class that has been detected. And now we will use a CV zone to draw the bounding box, and for that we will write CV zone dot corner rectangle. We are using the corner rectangle method provided to us by CV zone, and inside it we are passing our current frame along with the coordinates we got. We have x1 comma y1, which are the top left corner or the start of the bounding box, and also we have to pass the width and height of the object detected. And in the next line of code we have to show the confidence. For that we will use the CV zone put text method, put extract method, and inside it we will pass our frame along with the name that has been detected. We will write a formatted string so that we can see organized data. So what we are getting the name of the class or the name of the object that has been detected, and we will also show the confidence we have written as above. So we are getting confidence here, and we are printing our confidence over the bounding box we have. And outside this formatted string we have a tuple as x1 comma y1 minus 10, and we will provide the scale as 1. So the size of the text will be 1. If we decrease the value from 1, the text will become smaller. So this x1 is the bottom left corner start, and y1 also represent that, but we are subtracting minus 10 from it so that we position the bounding box slightly above top corner of the bounding box. So this x1 is the top left corner, and y1 also represent that, but we are subtracting minus 10 so that we can put the text little bit above the bounding box. So let us execute our file to see if we have successful to detect the objects and draw the bounding box around them or not. So we got into an error. So what is the error line? Let me see that. So the mistake I have found is that we have not make this value as integer, so it is unable to extract the value present at that index. So I think this will work now. Again we got into an error, and what it is saying, the line of code is we have the line as 18. Okay, we have missed a parenthesis outside of it because it is a separate tuple, or these are two parameters we are giving inside this corner rectangle. One is the image frame and the other one is the tuple of the bounding box, which contains the x1 y1, which is the top left corner, the starting of our bounding box, along with the width and height. So let's again execute the file with the hope that it will not show an error this time. You can see that the person has been successfully detected, and it is drawing the bounding box around that person. Currently it is a little bit slow, but if we use our GPU, this processing will become fast. And if I turn around, you can see that it is detecting the chair behind me. So let us put another object in the front. You can see that it is detecting as a book. So let us bring a bottle so to see it is detecting it or not. So you can see that it is detecting a bottle and also drawing the confidence over the corner of that bounding box. And also it can detect a laptop. So let's see, it is detecting this as a laptop. So this is how we perform the YOLO object detection, and currently we are using the default classes, and in the next file we will train our custom YOLO model and use that. So that is the complete real-time object detection in just few lines of code. And remember, this is the default YOLO model detecting from its 80 pre-trained classes. Later in this section we will go further and train our own custom YOLO model to detect the objects that does not exist in those 80 classes. So now we are headed towards training a custom object detection model. We have opened RoboFlow in our browser, and you have to just type RoboFlow in your search bar, and this platform will appear. You have to open it, and this RoboFlow is an online platform that helps you find, create and manage datasets for computer vision. It has a massive public library of pre-made datasets that people from all over the world have uploaded and labeled. Instead of spending days or weeks collecting images and label them by yourself, you can simply search RoboFlow, find a dataset that matches your requirements and use them. So why we need a dataset now? Because when we used the default YOLO model earlier, it already knew how to detect 80 objects because it was trained on thousands of labeled images of those objects. So training is how a model learns. You show it thousands of examples, like you say that here is a car, here is a dog, here is a bottle, and the model learns the visual patterns of that. So if we want YOLO to detect something custom that is not available in the 80 classes, let's say we have to detect a necktie. So for example, the necktie is not available in the 80 default classes of YOLO. What we will do, we will collect hundreds of images, combine them and label the necktie present in each image so that we can have a organized dataset, and then we will train our YOLO model over that dataset. So for the demonstration of this part of the course, we will train our YOLO model to detect thumbs up and thumbs down gestures, because we believe that training a model that will be able to detect the hand gestures like thumbs up and thumbs down will be a beginner friendly approach if you want to learn training a custom YOLO model. So we have to search for that dataset on RoboFlow. We will go towards explore, and here we have the search bar. Here we can write thumbs up and thumbs down. Sorry for the spellings, but several datasets has been appeared. You can see that this is the thumbs up and thumbs down dataset. You can see that name of classes and the number of images inside it. If we open the dataset, we can see that this is an object detection model, and it contains this number of images. And if we open any image, you can see that image is labeled. You can see that it is a complete image, but the thumbs up is the object that has been drawn out by a bounding box, and you can see that a label is appearing like that, thumbs up. And if we go back, we can see other images also. So this is the image. You can see that this is a complete image, and this is the thumb down gesture. So what we will do, we will use this data set and train our model so that it will perform the thumbs up and thumbs down gesture detection for us. So for getting the data set, we have to go to this dataset section. And for training the model, we need a platform. Just like we are using PyCharm, which is IDE, integrated development environment, where we can develop our Python programs. So we need a platform where we can train our model. So the name of that platform is Google Colab. It is the product of Google. You have to type Google Colab in your search bar, and this platform will appear. You have to open it, and it contains the notebook. It is the same environment as we have the Python environments, but it provides you GPU support along with the RAM, so you can train your model fastly. We can also train our model locally, but training on Google Colab is the beginner friendly approach, and it takes less time. As we are training our thumbs up and thumbs down model, so on Google Colab it will takes about 30 to 40 minutes roughly, and if we train it on our local PC, on our CPU or GPU, it will consume an effective amount of time. So that we have picked our medium as Google Colab, and what we will do, we will get our dataset from here. We will create a notebook inside our Google Colab and use that dataset to train our model. So we will create a new notebook from here. So this is the user interface of Google Colab. Here we can select the environment type that we want to connect. Let's say we can go to this change runtime type, and from here we are selecting the GPU. This is the free runtime environment provided to us by Google Colab. We can also use CPU, but it is very slow. So we will go towards this GPU option and hit save, and after saving that you have to connect it so that your medium gets active, so that whenever you write the code and execute, it will perform the tasks for you. In Google Colab, the code runs cell by cell. So this is a cell, we need a code. So we will go towards our data set, and from here we can download our data set. Whenever we click this download button, it can say that you can also train the model over the RoboFlow. So RoboFlow provides you to train the model, but in free tier you are not able to train a model, so you have to download your data set. You have to click that, and then you will get two options. You can download a zip to your computer so that you can train your model locally on your PC. You have to download the zip, but we are training it in Google Colab, so we have to use this custom code, and we will select this option, show download code, and hit continue, and we have to select a format. And as we know, we are working on the latest format of YOLO, so we will select YOLO 26 from here, and also we will hit continue from there. You can see that it will generate a downloading code for us. So this is the downloaded code for us. We will copy it from here and paste it in our Google Colab. So this is an API key, it is confidential. This is a not good practice to show your API key to the other persons. For educational purpose, I am showing this to you, but this is not a good practice. So this is a one cell. This cell contains the code where it will download the dataset that is available on RoboFlow. This code will download my dataset in this current working directory. Currently it is empty, and let me click this. We have completed the captcha that appeared suddenly, and now we can see that this is the root directory of Google Colab. There is nothing appearing here. Sample data is some files that it uses internally. We are not concerned with it. We will download our dataset here. So this code will create a directory here, and after downloading the dataset, we have to train our model. So whenever you go to this hover this section, you will get a new cell, and here you can paste your training code. So you can train your YOLO model with very few lines of code, only this. You have to initialize a YOLO model. You can see that YOLO 26 as small. So currently we are training as a small model so that it does not consume too much time. And below it we are using this train method provided to this model, which has been initialized by YOLO, and inside that we are passing the data over which we have to train, and then we have to pass the number of epochs, then we have to pass the image size, and also the batch. Epochs is the number of iteration you perform to train a model. So for example, this is just like learning a lesson. For example, my teacher said me that you have to learn this lesson 50 times, then you will remember it firmly. So that what we are telling to the model, that you have to pass the whole images from your neural network so that you can learn the images or the visual patterns of the images very well. So what are the images? We have the thumbs up and thumbs down images. So what we are doing, we are passing whole images from the network or the model we are training 50 times, and the image size we are passing that we resize our images. So let's say the RoboFlow has uploaded the images in some other size, we resize them into 640 by 640 pixel ratio, and then we are passing the batch size. So batch is telling that how many images will be passed at a single time. So we are defined that batch as 8. That means 8 images will be passed collectively, and then the next 8 images, and then next the 8 images. So let's say there are 500 images in your data set. These images will go into the model one by one in the batch of 8, and when whole pass is completed, we say that we have completed one epoch. So like one epoch, we have to perform 50 epochs. It is a time consuming process. As I've told you that it takes 30 to 40 minutes roughly. So we have to execute this cell, and you can see that it will create a folder here that will contain my downloaded dataset. You can see that it has successfully installed, and no, it is not successfully installed, it is running. So now we are done. You can see that this green tick is representing that this cell has been executed. we will hide our output, and you can see that this folder has been created. This contains our images, and inside the train folder we have all the images that were available on RoboFlow. So we will use these images to train our custom model that will detect our hand gestures of up and down. So this is the test folder that contains also the images, because whenever we train a model, we divide the images into three parts. The major part is the train part that contains 70 to 80% of the images, and then we have the testing images that will be used to test the model when it is trained, and then we have a folder of valid that will be utilized when we are training the model and the model is not improving. Then we use to this valid data so that it can validate the model training. So this validation folder or the valid folder will be used during the training, and when the model is trained on the training data we have here, we have to test that model that it has correct or not. We have to use all the images inside this test subfolder. So we will close this now and we will start training. So when you start training, there appears a runs folder from where you can download your model. In the very first line of this train, you can see that we have a parameter as data and we have passed a file name as data.yml. This points to the data.yml file that came with the RoboFlow download. It contains path to the training and validation images and names of the custom classes. In our case, we have thumbs up and thumbs down. If we open it, we can locate our data.yml file, and if we double click, it will be opened, and you can see that it has divided all the images into three parts, which is the train, where these are the main images on which our model will be trained. The validation will be used to improve the model training, and the testing will be used to test the model after training. And you can see that in the names list we have passed the names of two classes that we are going to detect, which is the thumbs up and thumbs down. So this is the data.yml file and we are training our model over that. So we will execute this cell from here, and it is saying that no module name Analytics has been found. So we have to first install it. We have to use this notation. Whenever we run or install any library in Google Colab, you have to write this exclamation mark and then install, and after that you have to write the library name you have to install. So we will hit enter. It will install the Analytics. Then we can successfully initiate our model training. So now we will execute this cell. Cell execution has been started and we are now able to see what is happening inside the output box. It again give an error because we have not set the path of our data.yml. We have to copy the path from here. You can see that data.yml. We have to copy the path and paste it inside here so that it can train well over the data that we need to be trained. So now training has been started and it is downloading the Analytics assets what it needs and the other things with that, the validation, the optimizer, and it start running the epochs. As I've told you that we have to pass whole data 50 times from our model so that it can learn the patterns. So you can see that it is running the first epoch. It is a slow process and it is really time consuming, and when you are done with your training, it will automatically create a folder named runs, and inside that runs a model will appear. If we go inside the detect, you can see that it is appearing, and inside the train then we have the weights folder, and then we have to open it also. It does not contain anything yet because it is training. Whenever the model is trained, inside the waist there appear a model with the name of best.pt. You have to download that will be your custom model. So let's say we assume that our training has been completed. Because it is time consuming, we are not spending too much time here. We will go towards learning our next section. So for the sake of understanding, I am telling you that when the whole cell is executed, this weights will contain a file name best.pt. You have to download that file. That is your model. As I have said you that you have to download that best.pt file, we can see that I have downloaded and placed it inside our current working directory. Now we don't need to change anything. We can use our previous code. We just have to alter the model name. Previously we were using the YOLO26 default model. Now we have our custom model that has been trained, and we have downloaded this bash.pt. We just have to change the path. So YOLO will use this model to perform the gesture detection for us. So we will execute our file without changing anything more. You can see that the webcam has been opened, and if you can see that it is successfully detecting my gesture. So this is thumbs up with the confidence being printed over the bounding box, and this is thumbs down. And if I do any other gesture, it will not detect it. You can see that. So it is only detecting the thumbs up and thumbs down. So this is the custom object detection we have performed. We have used YOLO, and we went to RoboFlow and got a data set. We trained the model over that, and hence we have our custom object detection model. Welcome back to the Modern Computer Vision course. So far we have covered two major sections of this course. In basic vision, we have learned how to read, manipulate and process images, and then in real-time vision, we have built live detection systems. Now we are moving into the third and final section of this course, which is AI vision. In this section, we will be using pre-trained AI models provided by Microsoft, Facebook and Stable Diffusion, and all through Hugging Face Transformers, which is a Python library that gives us easy access to use these ready-to-use models. We will cover three things in this section. First one is the text detection. We will extract and read the text from any image using AI. The second thing we will perform is the semantic segmentation. So instead of just drawing a bounding box around an object, this tells you exactly which pixel in the image belongs to which object. So it does not just tell you that there is a person in the image, it precisely outlines every pixel of that person. And also this semantic segmentation will generate the mask of the object that has been detected from that image. So that mask will be usable for the next and third approach we will be using, which is image inpainting. We will use stable diffusion so that we can edit images intelligently. For example, we have to remove a person from a photo, and also we can change the background. And so let's get started. And you can see that we have already created this C_AI_vision subfolder inside the root directory of modern computer vision, and inside it we already have a folder of images. These are all the images we will be using inside our Python programs for this section of AI vision. So we will create our first Python file with the name of text_detect and hit enter. We will start writing code by performing the imports. So the first import we have the import of transformers. So transformers is a Python library made by Hugging Face. Hugging Face is a platform that hosts thousands of pre-trained AI models from Microsoft, Facebook, Google and many others. This transformers library make us able to load these models and use them directly in our Python programs. And we are importing the pipeline from this transformers library. So this pipeline is a high level utility inside transformers that wraps a model and all its processing steps into single callable object. You will tell it what task you want to do, give it a model, and it handles everything else. You can see that currently it is showing a red warning because we currently don't have installed transformers in our virtual environment. So for that we have to go to our terminal. We will use a pip command to install transformers. We will write pip install and the name of library, which is transformers, and you can notice that I have mentioned a specific version of transformers because this version of Python which we are currently working with, which is Python 3.13, this works best with this specific version of transformers. So you have to install this version of transformers to avoid any problems. We will hit enter and wait for few minutes because this is a time taking process. Library has been installed and the red warning has also been disappeared. So now we will load our model by creating a pipeline for text detection. For that, we will write this line of code. We are calling the pipeline method we have imported from transformers, and inside it we will pass two parameters. The first one is the task we will assign, that it has to perform a task from image to text conversion, and the second thing we have to mention the model name. So this is the model provided by Microsoft and its name is TROCR. This model is hosted on Hugging Face and specifically trained on read printed text from the image. You can see that the name base printed, that means it is specialized for reading the printed text from the images, and this TR stands for Transformers Based Optical Character Recognition. When you run this line of code for the first time, it will download the model from Hugging Face and cache it in our machine. So for the next run onwards, it will load that directly from the cache. Now let us go towards running the model on our image. So for that, we will write this line of code. We are calling that pipe we have created as above, and inside it we have to pass the image from which we want to extract the text. So let's say we use this image. We have to provide the path. So this pipe will load the image, process it through the model, and returns the result. So we are saving the results inside this variable, and now we have to print the result in our terminal. We will use result and we will target the first text we have read from that image, and we are targeting the generated text from that dictionary. As we know that result is a list because we use the same list in the YOLO detection, and we are taking the first item out of it. You can see that we are targeting the 0th index and it will give us the first item, which is a dictionary, and from that dictionary we are pulling the generated text key. It will give us the value of the key with the name of generated text. So it is nothing but the generated text the model extracted from the image. So the image we are using is this one. So in this image you can see that computer vision helps machines to see. So we will execute this file to see if our code is working fine or not. So this gave us an error of a valid path to the image. So let's see what is that error about. What if we remove this CI AI vision from here, and now we will run our code to see the results. Hope so it will work now. So these red messages are diagnostic logic messages from Hugging Face. We don't have to worry about them, and it is the output we got from the model. You can see that it has printed the output successfully, like computer vision helps machine to see. If we see in the image, you can see that it is the exact text that has been extracted out of that image, and we have done this thing in 4 lines of code. We don't need a huge code base or any complex model to do this task. But there is an important limitation of this approach, because the pipeline we have built works well, but it is designed for single line text. As you can see, if we see in this image, this is a single line text, and if the image contains multiple lines, it will either miss the lines or give us some random result from that image. So let's see what does it mean. Let's say we use this image. So you can see that this is an image and this contains multiple lines. But if we try to read this image, and let's see what the results it will give to us. So these are again the logistic message, and it is extracting amount, even though amount is not present inside this image, but the model is hallucinating because it is built for single line text, and we are passing an image with the multiple lines, so that's why it is not working fine. So for detecting multiple lines of the text properly, we need a more capable model. We will use the model that is also provided by Microsoft, but the name of that model is Florence 2, And instead of this pipeline, we will use the auto model for casual LM and the auto processor directly. So let us update our code now so that it can read the image with multiple lines. So first we have to tweak our imports. So why did it imported CV2? I don't know. Maybe while writing the code I have written it mistakenly. So the first import we need is from PIL import image. So here we are bringing in the image from PIL. PIL is the Python imaging library, and the model I have mentioned, which is Florence 2, does not accept a file path directly. Like we are passing this file path directly, we cannot do this thing with the Florence model. So that's why we are using the image object from this PIL library, which is Python imaging library. And then we have to update this second import also. We have to remove the pipeline and we need auto. This is the import we need, and the second import from this same transformer library is the auto processor. And now we will load our image using the image object from PIL. We will write a variable as image, and here we will use image which we have imported from here, and we will open and we will give the path. So we can copy the same path we have given here. This dot open method will loads the image file from the path, and it ensures that it is in RGB format. And now we have to load the processor and the model. For that we will write this line of code as. So this is the name of the model we will be using, which is Florence 2, and the other parameter we will pass is trust remote code, and we will pass true to this. So this from pre-trained downloads and loads the Florence 2 model from Hugging Face, same as before. First we have to run it. It will download it in our cache and it will be used onwards. And the second thing we have is this trust remote code that is required here because the Florence 2 uses some custom code that ships alongside the model weights on Hugging Face. So in short, it flags the transformers library to trust and execute the code. And after the model, we have to load our processor. We will write this line of code. This is how successfully we are loading our processor for the same model. This processor is essentially the model's input and output handler. It knows exactly how to format your image and text prompt before feeding it into the model, and how to decode raw output back into something readable. Now we have to prepare the inputs, and for that we will add this line of code as input equals processor. So here we are calling the processor with the three arguments. The first one is the text argument. It is a task prompt for the Florence 2. This Florence 2 is a multitask model that can do many things. So here we are telling that what you want to do with that model. We want that Florence 2 to perform OCR with the region. In simpler terms, it is saying the model that you have to read all the text in the image and also tell us where each piece of that text is located. And the second argument we have of this images, and we are passing the image we have opened here using the PIL library. And the third thing we have this return tensors, and we are passing the value as PT, which tells the processor to return the input as PyTorch tensor, which is the format that model expects. Now we have to run our model, and for that we will write this line of code. This model.generate runs the actual inference. We pass in our prepared inputs using the double static inputs we have got from here, and here we are unpacking using the double statics to unpack the dictionary directly into the function. And the second parameter we are using of this max new tokens, and we are passing the value of 1024, which sets the maximum length of the output. And since our image could contain many lines of text, so we give it a generous limit of 1024 tokens, so nothing gets cut off. But this model's raw output is still in the tensor format. We need to decode back into the text. For that, we will write this line of code. So this batch decode converts the model's output tensors back into a readable string, and we are setting the skip special tensors as false because the post processor needs them to understand the structure of the output. And this batch decode converts the model's output tensors back into the readable string, and we are setting the special skip tokens as false, and we are taking out the 0th index because the batch decode returns a list and we are only have one image. Now we have to organize our decoded text so that we can see it. For that, we will write a line of code as result equals So this post-process generation takes the raw decoded text and structures it into a clean organized data. We pass in the task name again so that it knows how to parse it, and the image dimensions so it can correctly map the bounding box to the actual image size. Now we can remove these two lines of code as these are not usable now, and it's time to print the result in our terminal. So for that, we will use a for loop, and I will directly paste the code manually because this is a huge code and there is a possibility of an error. To rapidly wrap this up, I have pasted it directly, and we are pretty much done with our code. By using this for loop, we are accessing the result using our task key, which is this OCR with origin, and inside it there are two lists. One is the labels and the other one is the quad boxes. This labels contains each piece of the detected text, and this quad boxes contains the coordinate of where the text is in the image as a 4-point quadrilateral box. And then we are using the zip method to pair each label with its corresponding box and loop over them together. And inside it we have this print statement and this notation with angle brackets enclosed with a slash and s. It is the end of sequence of the special token that sometimes appear in the label string. We remove it with the replace we have here, and we are cleaning it using the strip method. So let us execute our file to see that if the code is successful for extracting the text of the multi-line image or not. So it is telling that some packages are missing from it. So we will run this command inside our terminal. These are the additional dependencies that this Florence model need. So we have to go to our terminal and we have to paste that command. Now we will again execute our code file with the hope that it will work fine. Now it has given another error on the line 17. So let us debug that error also. So where is the problem? So this is here. We have forgot to add the angle brackets, so we add that again and let us execute the code. So now we have the successful execution of our program. So first let's see what we have inside the image. So this is the image, this is the main text, then we have a pip install command, and then we have these bullet points. So what we got in the output, let us execute the file again to see the results, if it is successfully read all the text from the image or not. So it has been executed and you can see that it is printing CV zone with all its coordinate where it has been detected in the image, then the pip install CV zone, and all 5 bullet points with the hand tracking, face detection, face mesh, pose, and classification. So this is the successful execution of our program in which we are detecting the multi-line text from an image. Now we are moving to semantic segmentation. For that, let us create a new Python file inside our AI Vision directory, and the name of that file will be semantic underscore segment. But before we write any code, let me quickly explain what semantic segmentation actually is, because it is quite different from what we have done before. In object detection with YOLO, we draw a bounding box around an object, a rectangle that roughly surrounds it. But semantic segmentation goes much deeper than that. Instead of a box, it identifies every single pixel in the image and labels it. So if there is a person in the image, it does not draw a bounding box around it. It colors every pixel that belongs to that person. If there is a sky, every sky pixel get labeled. So eventually it will generate the mask of the detected image. It is nothing but the labeled each pixel of that image. This is why it is called semantic. It understands the meaning of every part of the image. And the model we are using for this Python program comes from Facebook, and the name of that model is Mask to Former, one of the strongest segmentation model available, and it is hosted on Hugging Face. So we will start writing code by performing our imports. This is the same as we used in text detection, the pipeline which comes from transformers library. And the second import we need is the import of image object from PIL library. And now we have to load our model using this pipeline. For that, we will write a name, variable name as pipe, and here we will call this pipeline method. And inside it, we have to assign a task. So this time we need image segmentation. So for that, we will write image dash segmentation, and after the task, we have to mention the model name. So the model we will be using, so this is the model name which comes from Google, and the name of that model is this one. So let us execute our file to see that if we have written the name as correct or not. So there is no error. It is a warning message. We can ignore it also. So we will now load the segmentation pipeline. And for that, first we have to open our image, of which we need the semantics. So we will create a variable as image, and here we will use image dot open, and inside it we will pass the path. Let's say we will be using this image, and we will using the path of it, and we have to append the name of the folder that contains that image, and we have to convert that image into RGB. Now we have to run our segmentation, and for that we will use the same syntax we have used in previous codes. We will write pipe, and inside it we will pass the image which we have opened using the image object by PIL. It will make the model to analyze every pixel in that image and groups them into segments and returns the results. And it is storing the results inside it. So results become a list, and each item in the list represent one detected segment found in the image. Now we have to read and save the results. So for that, I will manually paste a for loop to get rid of any error. So we have to match the variable name as a result. In the first line of this for loop, we are looping over all the detected segment. Each segment is a dictionary representing one labeled region found in an image. And then we have this long print statement, and it is printing two things. One is the label and the other thing is the score, because each segment has two key pieces of the information. The first one is the label of the segment, and the other one is the score of that segment. So the name can be the object that has been detected. So it can be a person, sky, floor, tree, and like that. And score is the confidence score. And then we have this notation. Here we are formatting it into a 2 decimal places. And with this line of code, we are saving the masked image. Masking is nothing but labeling of every pixel of that image. So what does that mean? Let us see by executing this code. So we got into an error. So the path name we have written wrong. Let me see this, and it is images, not image. So we will execute it again. Now the objects that has been detected out of that image is a bench, a tree, sky, grass, plant, and a path. So let us see that image. So the image is semantic segment image 1 and we will open this image. You can see that we have applied semantic segmentation over that image, and if we execute our file again to see what the semantic segmentation detected out of our image. So it is telling that there is a bench. We can see that there is a bench available, and let me scroll it down. It is telling a bench is available with the confidence score of 1. 1 means 100%. There are tree available, there is some sky visible, and this is some grass, plants and path. So this is the successful semantic segmentation, and if we look into our working directory, it has generated the mask of each object. So you can see that this is the bench, and it labeled every pixel of that object. So here is how we created the mask for bench, the same mask for path. If you open that, you can see that the mask has been generated for the path, and the mask for sky, and for the trees we have. So these masking images will be used further in our image in Paint, where we have to remove a specific object, because for removing an object or manipulating an object, we have to get all the pixels of that image. So this masking will help us further. We are going to implement image in Painting using Stable Diffusion. For that, we will create a new Python file inside our AI Vision directory, and the name of that file will be image_in_paint. And before we write any code, let me explain what we are working with. Actually, Stable Diffusion is a powerful AI image generation model. Most of people know it for generating images from text prompts, and you described something in words and it creates an image for that. But it can do much more than that. One of its capabilities is inpainting, which means you give it an existing image, mark a specific region you want to change or remove, and it fills in that region intelligently based on your text prompt. It does not just erase, it understands the surrounding context of the image and reconstructs what should be naturally there. Keep this idea of reconstruction in mind, because it will clear a doubt at the end of this section. And the model we are going to use is Runway ML, provided to us by Stable Diffusion, and it is a version of Stable Diffusion specifically fine-tuned for in-painting tasks hosted on Hugging Face. And now we will start writing our code, and we will start with the imports. The first import we have of this diffusers library, which is another Hugging Face library specifically built for diffusion models like Stable Diffusion. And the second import we have the import of image object from PIL library. And the third and new import this time we have of PyTorch. PyTorch is a deep learning framework or library that Stable Diffusion runs on. But here is something important. Actually, PyTorch is hardware specific. When you installed Ultralytics earlier in this course, PyTorch was automatically installed as a dependency. But that version is the CPU version by default. And if you have a GPU and try to run Stable Diffusion with that CPU version of PyTorch, which is downloaded by default by Ultralytics library, you will get an error when trying to move the model to CUDA. So the correct approach is to first uninstall the existing PyTorch and then go to the official PyTorch website, and from there you can see the commands to install the PyTorch according to your hardware. And for that I have opened the PyTorch website in my browser, and you can see that this is the command to install the PyTorch. And if you only have a CPU, you will use this pip command, and if you have NVIDIA and also you have the setup of CUDA, you will go to this tab and copy this command to install the PyTorch so that it can run on your GPU. What it will do, it will move your in-painting pipeline from CPU to GPU for having a fast computation process. We will copy this command from here and go towards our PyCharm terminal and paste it inside here. You can see that I have already installed for testing purposes. I am again installing it for demonstration purposes, so you will have to install it according to your device. If you have a CPU only device, then you can use the other command, which is this one. And if you have a CUDA setup with the NVIDIA GPU, you will use this command. And after discussing the import, let us write the code for loading our model. We will create a variable named pipe, and we will call our stable diffusion pipeline that we have imported, and we will call its method as from pre-trained, and inside it we will pass the name of model we are using, which is Runway ML. And this from pre-trained method downloads and loads the stable diffusion Inpainting model from Hugging Face. Whenever we execute this file for the first time, it downloads the model from Hugging Face and loads that into your PC cache. And later on, this model will be used from the cached memory. And the second argument we should pass inside this from pre-trained method is the PyTorch data type. This torch.float16 means we are loading the model weights in half precision. Using 16 bits per number instead of standard 30 bits, this cuts the model's memory usage in half. Because stable diffusion is a heavy model and float16 is what makes it fit in comfortably on our GPU, we will have a fast computation and get the results faster. And after that, we have our next line of code, and we will use the same variable, and we will use pipe to the device we have, and as we have a CUDA setup, I will write CUDA inside it. CUDA is NVIDIA's parallel computing platform which allows your GPU to run these calculations. And we have this line of code in which we are piping it to this CUDA device, which moves the entire model from CPU RAM onto the GPU volatile RAM. So all processing happens on the GPU. This makes Inpainting dramatically faster. And you can notice that we have assigned values twice to this pipe. Actually, in the first assignment, we are loading the Inpainting model, and in the second assignment, we are moving it to the GPU. And at this point, this pipe is our finally GPU ready Inpainting pipeline. And now we will load our original image along with the mask. As I have told you that mask is the pixelated area that will be used to manipulate an object present in an image. Let's say we load an image which is this park image, and we also have the mask of this bench object. So what we will do, we will pass a prompt to our stable diffusion model to remove this bench from this image. So for that we need the mask, which is the pixelated area of that object. So we will load both images, which the first one is the original image and the second one is the mask of that object we want to manipulate. And after loading both images, we are converting them to RGB, and also we are resizing to the 512 by 512 size. Now we have to run the inpainting process, and for that first we have to craft a prompt. We will paste the prompt, and in the next line we will run our inpainting model, and we will save the running result inside this results variable, and the arguments we will pass is the prompt, and inside the prompt we will pass the prompt we have crafted as above, and the second parameter is the mask underscore image, and it will take our mask we have created here from this one. Let me see. So this is the mask of the bench, and we are using it inside our code, and along with the mask we have to also pass the original image, and inside it we will use that one we have created as above here. And finally we will call this images, and we will target the 0th index. And what is the meaning of this images sub 0? We are calling the 0th index, which will take the first image which is inpainted. In fact, that is our result that we want to get. And after getting the result, we have to save that result somewhere. We will use a method named save. Inside it we have to pass a name with which we want to save that file. Let's say we want to save our result with inpaint underscore output dot png, and after that we will print a statement to see that we have a successful execution or not. For that we will say that so the prompt we have here is the empty park with green grass and small rocks along with the edge, no bench, no furniture. So what we are saying it to that, you have to remove this bench from this image. So we are pretty much done with writing our code. So we will execute our file to see that if we are successfully performed the inpainting or not. I have noticed that the pipeline components have been successfully loaded, but there is no output being shown. That means our program is halted in between, and let us stop the program and we will run it again to have our work done. You can see that our program has been successfully executed and we have saved the inpainted image. So let us see our inpainted results what we have. So the inpainted results are not so affected because what it does, it removed the previous band and generated a new one. Actually, this is a completely normal behavior, and here is why it happens. Stable Diffusion is a generative model. It does not just copy pixels from surrounding areas, it actually generates new content based on your text prompt and the context of the image. This is the nature of generating inpainting. It interprets the context and generates something plausible, not necessarily an exact reconstruction of what was behind the object. Sometimes result is perfect, sometimes it's at something like this. We can try adjusting our prompt to be more specific so that we can have the efficient result. So likewise, you can see that I have updated my prompt as remove the bench. Or another way to fix your inpainting is to run the pipeline multiple times, since Stable Diffusion has randomness built on its generation process and each run produces a slightly different results. So we have to run our program again and again until we achieve our goal. As I have executed my file again, and now I have improved results. So let us see what it has generated now. Now after removing the bench, it has placed a rock instead of it. This is the far better response than the previous one. Again, we can achieve more perfectness by making our prompt better. We can craft our prompt using an AI model. We give a command to an AI model to craft a prompt so that we can remove this object successfully. And also we can run our program again and again to have the enhanced result. So let us try this on a new image. This time we will use this one and we will try to remove this person from here. We will change the name of file and also the prompt. So this is our updated prompt. We need an empty autumn road with yellow leaf trees and fallen leaves and no person. Currently it have a person, but we don't want a person, so that's why we have given this prompt to inpaint, and let us execute our file to see the results. Again, our file has been successfully executed, and now we will see the inpainted results we have. So where is that one? So here we have. So these are the best results we got among all we have performed. So this is image inpainting and the final program of this course. We have combined everything from this section: Hugging Face models, PIL image handling, semantic segmentation, all working together. And this wraps up the modern computer vision course. Let us quickly look at what we have learned across the three sections of this course. In basic vision, we started from ground up, reading images and videos, manipulating them with grayscale and blur, cropping, and detecting colors and shapes using the HSV color space. In real-time vision, we have built live detection systems like face detection, hand tracking, body detection, background removal, and object detection using YOLO. We also went further and trained our own custom YOLO model to detect objects that does not exist in the default classes. And finally, in the AI vision, we work with state-of-the-art models from Microsoft, Facebook, and Stable Diffusion for reading text from images, segmenting every pixel of a scene, and intelligently removing and replacing objects using Inpainting. Now let us talk about what you can build with all of this. With face and body detection, you can build attendance systems, security camera monitoring, or fitness tracking apps that count reps and analyze posture. With hand detection, you can build gesture control interfaces, controlling your computer, a presentation, or a robotic arm with just your hand movements. And with custom YOLO training, you can build quality control systems for manufacturing, detecting defects of products, or even inventory management systems that automatically identify and count items. With text detection, you can build document scanners, receipt readers, or tools that can extract information from any image automatically. And with Inpainting, you can build photo editing tools, content removal pipelines, or image restoration systems that fix damages or unwanted parts of a photo. The skills you have now cover the full spectrum of computer vision, from basic image processing all the way to AI-powered scene understanding. Everything from here is about applying these tools to the problems that interest you. And good luck with whatever you build next.